Hi guys, we are going to start now the distribution grid part. So we are going to model and analyze how the distribution grid works and mostly understand how to control the voltage and make sure that the components, transformer and so on are not overloaded. We are going to use Simscape Electrical, which is an add-on in Simulink with a lot of pre-built components, power system components. So as we saw in the previous class, we were using, let's say, the normal voltage drop, the normal home lows to calculate voltage drops and so forth. And now what we want to do is to verify this calculation by building the model in Simulink, in Simscape Electrical. So the model that we will build is basically the same that we used for calculating the voltage drop. So we're going to have a certain voltage source, an external grid that is setting a certain voltage. At this point in time, let's not consider any transformer. So at this point in time, let's just assume that our main voltage has a 0.4 kilovolt. We take the cable, three-phase cable. Everything here is a three-phased balance system. We don't have any single-phase loads. And then we're going to have a three-phase balance load as well. So in the example, in the numerical example that we discussed last week, we had basically three cases that we wanted to analyze. The first one was a pure active power load, 100 kilowatt and no kilowatt. Let's say half active power and half reactive power, so 100 kilowatt and 100 kilovolt ampere reactive. And the last one is 100 kilowatt and 100 kilovolt ampere capacitive. Remember that for the load, it's using a load convention, so positive reactive power, it's inductive power. Yes, and we are going to basically see this free example and double check the calculation that we did by hand, basically using the classical formulas with the results that we have in Simscape. So we open our model. Just remember that all the Simscape components can be found here under the Simscape library, electrical, and then specialized power system components. And then we have the most important, let's say, the blocks that we will be using, which are not that many actually. It's the voltage source, the transformer that we'll see in the next example, the load, and the cable, and then some measurement points. So a quick look at the system. We have our external grid here. So this one is modeled as an ideal voltage source with, let's say, infinite inertia. So that's the frequency is not going to change under any circumstances. There is an impedance. So it's an ideal voltage source with an impedance in series. The impedance is characterized by a certain power, by a certain short circuit power, and a certain ratio between the reactance and resistance. So actually this value here is very high for a low voltage grid, but let's just keep it as it is right now. That basically means that the voltage that we will measure here at the terminal and the voltage, the internal voltage, will actually not differ that much because these two elements will be very, very small. Remember that the tool itself is designed for the American frequency, so you always come preloaded with 60 Hz, so always remember to change it to 50 Hz in case you want to analyze a 50 Hz system. The other important thing here to set is just to select that this element should behave as a swing or slack bus for the load flow. What else we have? We have the cable. The cable is let's say a standard pi representation of the cable with a series resistance, a series inductance, and a shunt capacitance. The values are given for the sequences, so for the positive and the zero sequence. yes, just make sure to put the values, the correct number. I mean, you see here it's in ohm per kilometer, it's in Henry per kilometer, so not ohm. Remember that there should be the 2 pi 50. Basically, if you are taking the values that are in ohm, the frequency here in the capacitance here as a farad over kilometer, and then the length. The load, finally, the characteristic of the load, it's a nominal frequency, nominal voltage 400 volt, nominal frequency 50, and then depending on the value that you want to analyze, whether it's going to be let's say a pure active power load as this one, so that would be 100,000 kilowatt watt and a 0 kilovolt ampere reactive. These values, the voltages and the angle, will be set as a result of the load flow, so we don't need to set that. It will come in the moment that we run the load flow. The measurement point, as we discussed, we have basically two measurement points. The first one is a measurement point that only applies for the load flow. So it's just a visualization of the load flow result. And the second one instead is a measurement that gives us the possibility to take voltages and current to be used during the dynamic simulation. So in this case, I just set the voltage values to be phase to ground, and the current, just the current going through the one of the phase. Remember, we have a fully balanced system, so it doesn't make any difference which phase I take. Also, I don't have the neutral. Again, it's not important because I don't have any unbalance. But keep in mind that I don't have a neutral, and I have a grounded system, meaning that I cannot easily assume that the phase to ground and the phase to neutral would be just the same voltage. Yes, so that's the view. If we want to run load flow, we need to open the Power GUI. We need to specify that we want to do a phasor simulation, that we want to perform a load flow. The settings are just this one that we change in order, since it's a small system, we don't need a very high base power, and we don't want to have results displayed in megawatt. And then if we want to open the load flow, you see that it's not a very complicated load flow to run because there are just two nodes. We can compute and then just apply the results to the model. Right now, nothing has changed because it was already preloaded. But the important things to remember is that one thing is the load flow, which will influence the values that we see displayed here in this visualizer here. The other thing is the dynamic simulation. So the values that you see here reported in the plots and the scopes, they are based on the dynamic simulation. So if things change during the dynamic simulation, then these load flow results are not valid, or they will, I don't need this one now, they are not valid, they will just stay for the initial load flow. Yes, so I just run a 10-second simulation just because I want to also get a better overview of the different values. So what kind of plots and measurement do we have here? It's just voltages and currents, but it's important to remember how the values are given from the measurement. All the values in terms of current and voltage are given as a peak values. So this is quite important because if you want to have the RMS value, we need to divide by square root of 2. Also, it's a three-phase system, so there are actually 3 vectors here. So there are actually 3 complex numbers. It's a complex number because I decided that I wanted to have a complex number as an output. And that means that I will have a 3 set of values with, let's say, a real and an imaginary part. So that will be my current, or my 3 currents, actually. Then I can always get split. This complex number is a pure in just the module and the phase. Again, I can get the current the module of the current RMS value. So I need to go in module, I need to divide square root 2, and then I get that the current is 148.3 ampere on all the phases. The angle as well, since this one is coming out in radians, then I need to multiply 360 and divide 2 pi if I want in degrees. And I will experience that I have basically the free, since it's a balanced system, the difference will be 120 degrees between the phase on one current, the other, and the third one. The same for the voltage, keeping in mind that I have the phase to ground, which for me is basically the same as the phase to neutral. So if I want to have the phase to phase, I need to multiply square root 3 and I need to divide square root 2 because this is a peak value. And if I want to get it normalized, so in per unit, I also need to divide by 400 volts. And then I get my values here, my free phases here as a complex number. Same reasoning, I can always get the module and I can get the phase. And in this case, for instance, I'm displaying just a voltage RMS value for the individual phase. That's 224 volt. The same if I want to get the per unit value. I could actually just double check whether, since this is supposed to be a pure active power load, ideally the angle of the voltage and the angle of the current, there shouldn't be any difference between the phasor of the current and the voltage, so the angle difference should be equal to 0, and we see that for all the three phases, of course, the angle is very, very small, so actually it's basically a 0. And that would be for voltage and currents on the loads. The same, of course, applies for the voltage at the main grid. And the same we can do for getting power values out. So in this case, I just use this block that is called power, three-phase phasor power. It just needs to get voltage and currents, and then it will get displayed computed active and reactive power. And then I can do all the balances. So since this is a system with 3 components, basically, then I can derive what are the losses, so what is the power that is lost on this cable by simply doing the difference between the main grid and the power on the load. So I can see what's the active power that the main grid is supplying, what's the active power the load is consuming, and of course the difference, it's what the cable is consuming. And the same also for the reactive power. In this case, the load is not consuming any reactive power, but since I have a current on the inductances on the cable, then I have a certain amount of reactive power which my grid needs to supply. And the final point that we can see here is how to calculate the voltage drop, which basically would be the reason for having the model here, to make the comparison with the values that we had derived manually last week. So also in this case, I can basically take the individual voltages. I just need one phase, so that's why I use this demux here, because I don't, since the system is balanced, I don't need to do the same calculation for all the three phases. So that would be just a way to get again the usual per unit value. So this is my voltage on the main grid at the terminal, which is basically 1 active on the real axis and basically 0 on the imaginary axis, which makes sense because this is the slack node for me. So by default, this voltage should be 1 in per unit and 0 in terms of angle. That's because I set the slack to be in this way. And the voltage on the load, which we find here down below, it's mostly, it's not very displaced. Actually, the angular difference is very, very, very small. And then I can do all the usual mathematical adjustment in order to get the value that I would like. So I can just do the difference between these two complex numbers, and then I can get their difference in terms of per unit. I can get their difference in terms of voltages, keeping in mind that I am taking a phase to ground, dividing square root 2 because I want the RMS value, multiplying square root 3 because I want the phase-to-phase voltage. So I get this 10.67 plus 3.6 on the imaginary axis. And the same I can do also in terms of modules and also angle down here. So I can basically get the module and the angle of the difference between the vectors, again in per unit, in voltage, and in degrees. And then I can also do the difference between the modules actually. So this is quite tricky because in one case I'm doing the difference between the two phasors here and then getting the module out of it. In the other case, I'm actually taking the module of the individual vectors and then doing the difference between these two, which in the end is the voltage drop, so to speak, that that really counts, that the one that is really affecting the power quality. So coming back to the slide, we basically see the results here. So this one was just the calculation that we did by hand using the formula, which is just a derivation of the Ohm law for this particular case. The, let's say, complete formula that would include whole voltage, the whole voltage drop, and the simplified formula which just include instead the real part of the voltage drop. And we get here the results. The one on the complete formula would be 10.96 volt. The one on the simplified formula, in both cases always assuming that I'm dividing by the nominal voltage, so 400 volt. And then the voltage drop that really matters, which is the one basically between the modules of the sending voltage and the receiving voltage, which is the 10.64 volt, which I get here. There is a small approximation error. And that would be for the first case. And then the other two cases to be compared, they are quite intuitive, in the sense that I can create the other case where I have 100 kilowatt and 100 kilovolt ampere reactive for the load. I need to rerun my load flow. Yes, and I can see now that the results here change. So as expected, since I got a fairly large reactive power consumption, then my voltage will drop as well. Then now I need to be careful, because if I want to run again my dynamic simulation, I also need to update this value here, because otherwise I will be in the situation that the initial value for the load flow will be 100,000 and 100,000 active and reactive, but then throughout the dynamic simulation this one will take over. So if these are not consistent, then there will basically be a dynamic. Yes, and I can rerun. I get the new simulation as expected. I have more power to supply, so I have also this bunch of reactive power, so the current gets larger. As expected, the angle, so the power factor, basically gets to 45 degrees, because it's 100 kilowatt and 100 kilovolt ampere reactive. Yes, and the power balances, I get more active power losses in my system because my current increased. So that means I have more joule losses on the cable. And of course, I also have a way larger than before provision of reactive power from the grid, because now I need to supply this 100 kilovolt ampere reactive. Again, I can do the same consideration on the voltage drops and just make the comparison between the values that I had in the second example. So again, the values calculated would be basically this 14.52 volt as a voltage difference that really influence our voltage drop in the system. And again, the comparison with the complete formula and the simplified formula here. And the final case would be to take the minus 100 kilovolt ampere reactive here. So once again, I'll run the load flow. As expected, the voltage is increasing, and it's actually even better than the first case, because this amount of capacitive power is helping to sustain the voltage. Again, I need to make the small adjustment here, and I can get the new case. The current, even though in terms of complex power, this case is similar to the previous case, because I always have 100 kilowatt and 100 kilovolt ampere. The difference is now it is negative, but it's still 100 kilovolt ampere reactive. The voltage is slightly higher. That means that the current will be a bit less compared to the previous case. The angle got minus 45 degrees because I have that the current now it's leading the voltage, and I can do again the same reasoning as before. In terms of losses, again, the fact that I'm sustaining the voltage is improving a little bit, but still I have a huge current flowing in the system, so this is not beneficial for the losses in the end. And the same for the reactive power. That means that I am producing this 100 kilovolt ampere here. The grid has to take basically all of them except for what is lost on the cable. And again, we can come down to the voltage drop calculation. So as usual, we can have the different values. As expected, the voltage drop is reduced compared to the previous case thanks to the capacitive support of the capacitor, of the capacitive side of the load.